minimize the videos here and start.
Okay.
Okay.
So today's speaker is Zach Nicolaou from Northwestern. So take it away, Zach.
Thanks. Hi, I'm Zach from Northwestern. Like Lachlan said, I've met Lachlan and George a few times at some previous conferences. So today I'll be talking about a recent paper from our group at Northwestern with Adelson Motter, critical switching in globally attractive chimeras. So let me give you a little background on my motivations and interest first, so you know where I'm coming from. I'm largely interested in pattern formation systems, so non-equilibrium systems which have been studied in the past, such as these Faraday waves. I took a video of this petri dish of water. In this system, we vibrate the surface on which the water is standing, and waves start to form on the surface of the water for sufficiently strong driving forces. So of course, the waves aren't that interesting in them of themselves, but the patterns that they form are interesting. You can see that there's some square array of peaks that starts to emerge, which is a little surprising given that the dish is circular. So one wonders where that square symmetry came from. And also there's questions of stability are of interest in these sorts of systems. So when is the state in which the water surface is flat? When is that stable, and when does it become unstable? Those are the sorts of questions that are interesting. So that field is mature by now. Pattern formation was studied in the 90s and 2000s and so on. Nowadays, the real question is how can we take advantage of pattern forming systems to create novel behaviors? So here's an example of a metamaterial, which was of interest to me in the past. This is a system composed of particles connected to neighbors. And as you stretch and pull this material, destabilization occurs, instability occurs in which the material contracts despite us trying to pull it apart. So this is negative volume compressibility, which is not possible in conventional materials because of thermodynamic restrictions, but in non-equilibrium systems, it is possible. So the motivation and the long-term goals are how can we control natural processes like pattern formation in order to design, self-assemble, novel, new things. So that's the broad background. But a little more specifically, in the last few years at Northwestern, I've been studying oscillator systems, coupled oscillators. So synchronization in systems of coupled oscillators. There's a broad interest in biological applications and also technological applications, and really almost any kind of system that has dynamics can often be modeled as a coupled oscillator kind of system. So of recent interest since 2004, when Abrams and Strogatz described them, are the Chimera states. These are states in which coupled oscillators exhibit identical coupled oscillators, importantly, exhibit coherence and incoherence simultaneously. So it's a symmetry breaking state in which identical oscillators form a cluster of coherence, which coexist with the cluster of incoherence. So these are specific examples that I've studied in the past. This top one is a continuous chimera in a continuous system. This is a locally coupled system in which it's used to model pattern forming systems like the BZ chemical reaction and more broadly other systems. This is the complex Ginsburg-Landau equation. So we can see there's a complex phase and amplitude. And in the center of this system that I simulated, there's a spiral, which is coherent, which is surrounded by incoherent asynchronous behavior, which is called defect chaos. So in addition to continuous coupled systems like the pattern forming ones, I'm also interested in locally coupled network models. This one on the bottom here corresponds to what we call Janus oscillators. These are oscillators which are, have a particular network structure, which are coupled to only oscillators which have a different natural frequency. So every oscillator, it's a bipartite sort of network structure. And you can see there's a big group of the oscillators moving around this torus, which are coherent. And then there's a number of them which don't form that group, but remain incoherent. So these are a few chimeras that I've studied in the past. And this is the sort of systems that I'm going to be talking about today. By the way, if anybody has any questions during the talk, please interrupt me as if this was a normal seminar. So what are we talking about today? Well, I'm talking about this paper, recently published in PRX, Critical Switching and Globally Attractive Chimeras. So here's the abstract and the authors. Yan Zhao Zhang is a recent graduate student at Northwestern who just defended his thesis. Adelson Mater is my boss, faculty at Northwestern. Raj Roy and Joseph Hart helped us out with some experiments from Maryland. So I highlighted a few words here in the abstract just to give you some idea about what we're talking about. We're going to be talking about chimera states that are globally attractive and they attract almost all initial conditions, but they exhibit some power law switching behavior. This power law switching makes them extremely sensitive to small amounts of noise. And that power law switching is unusual in the context of stochastic switching induced by noise, because normally we expect exponential scaling with noise intensity when we switch between attractors in dynamical systems. So part of our motivation is to try to understand how the power law switching emerges in the system. And what we find is that it's related to the chaotic behavior in the system, and in particular to these intermingled or riddled basins of attraction. So that's a big overview. Let me show you the details in this particular system now. So here's the model that we're going to study. We focus on maps of coupled rings. Maps meaning they have discrete time. X at t plus 1 is given by x at t. And rings meaning there's two rings. The superscript denotes the ring index, and the subscript denotes the oscillator index within the rings. So the bottom ring here, every oscillator is coupled to its neighbors, similarly with the top ring. But between the two rings, there's all-to-all coupling. In the right-hand side of this equation, there's a term corresponding to the intrinsic dynamics, which we take for the majority of the study to be a logistic map. So the logistic map is given by this function f of x, which is x times 1 minus x, and this parameter r. So in the absence of all of the coupling, each of these nodes corresponds to a logistic map, which could be chaotic depending on the parameters. So in addition to that intrinsic dynamics, there's the intra-cluster coupling terms. You can see there's a coupling constant sigma, and there's diffusive coupling. So every oscillator xi receives an input signal given by the same f from its two neighbors, and it has -2 its signal from itself. So that makes the coupling diffusive. So in addition to the intra-cluster coupling, there's an inter-cluster coupling, which has the same form. It's the difference between f of oscillator in ring 2 minus f of oscillator in ring 1. But the coupling constant is a smaller in the inter-ring case. So we take the constant c to be 0.2 just for concreteness, but the results don't change if we change c. So then finally, in addition to the network of coupling interactions, we have a Gaussian white noise term, or a Gaussian noise term. It's not white because it's discrete. Every oscillator receives its own independent noise signal. These are all uncorrelated with each other. Okay, so that's the system that we're considering. Here's the parameter space. R versus sigma coupling strength versus the R's, the intrinsic dynamics. And depending on the values of the parameters, we see chimeras, unsurprisingly, since I'm talking about chimeras. So I should mention why we study a system like this at all. This previous paper from all the authors except for me was a study on linear stability in cluster synchronization. So we designed this network to have a specific symmetry to it. In this case, you can rotate or reflect the oscillators in each ring. And we were interested in studying those sorts of systems because of their ability to form clustered synchronous groups. So we take advantage of the results in this paper to design the chimeras. In particular, we design them to be globally attractive by ensuring from the master stability formulation that both the synchronous and the asynchronous dynamics are unstable. So there must be a chimera which is globally attractive. So that was the first interest in studying these systems. But what we found, or what these authors found, was that the system actually exhibits much more complicated dynamics than they were expecting. So that was part of the reason why I got recruited to help understand this system. So what exactly is this dynamics? Well, the temporal evolution of these oscillators is described here. We have a error, synchronization error, which is the sum over all of the differences in the oscillators for each ring. So there's an error for ring 1 and an error for ring 2. So that's shown in the middle plots here. The top plot shows the top ring, and the bottom plot shows the bottom ring. So you can see that there's, when the orange error is small, all of the oscillators in the bottom ring are synchronized, and they all have the exact same value for xi, whereas the top ring has different values for each xi. So indeed, this is a chimera state in which half of the oscillators form an asynchronous cluster, and half of them form a synchronous cluster. But we can also see this error in the synchronous cluster fluctuates. And in particular, sometimes it gets quite big. And at that point, a switch occurs in which the roles of the synchronous and the asynchronous rings switch. So this switching, here's an animation of one switching event. Every oscillator's phase relative to this bottom oscillator is shown by the color. And you can see the left ring just became synchronous while the right ring is asynchronous. Now at this point, it's switching roles again, and now the right ring has become synchronous and the left ring is asynchronous. Let me play that again one more time just so you can see how it occurs. So the fact that the roles of the synchronous and the asynchronous rings switch in time is not in and of itself the interesting aspect. The interesting aspect is how frequently that switching occurs. It occurs much more frequently than we would expect. So we call that a critical switching behavior. And let me give you a little bit of background on stochastic switching theory for fixed point attractors. This is the theory developed by Riddled and Wenzel. And it tells us that if you have a dynamical system with two fixed points and a small amount of noise added to that system, we expect that there'll be switching in the dynamics between the two fixed points, which will occur at a rate which is exponential with the noise intensity. So the T here is the average amount of time that one has to wait to switch from one state to the other state. And the S here is a quantity which is called the quasi-potential, or the action. This is a potential barrier that has to be overcome by the noise in order for a switch to occur between the two states. And Xi here is the noise intensity. So as the noise intensity gets small, the average switching time gets very long because it becomes very difficult for the noise to overcome the potential barrier. So that's the standard idea of what we expect to happen when we have attractors in a dynamical system and we add a little bit of noise and observe how frequently they switch between the attractors. This quantity S, by the way, is called the action. Or this is the minimum of the action. So S is the quasi-potential barrier, it's called. It's given by the infimum over all paths that connect attractor A to attractor B of the difference between the actual trajectory and the intrinsic dynamics. So it's a sum over all of the noise, how far the noise took you off of the intrinsic dynamics. Anyways, this is an established theory for fixed point attractors. But we're not dealing with fixed point attractors. You saw before that the systems that we're looking at have dynamics and they're quite chaotic. We don't observe switching rates which decay exponentially with smaller noise intensity. Instead, we observe power law switching rates. So you can see this is simulations of our switching chimeras for different parameters. A very clear power law behavior in which as we decrease the noise intensity, the switching rate only decays with the power law instead of an exponential rate. So that becomes very significant for small noise intensities because very small noise can still induce switching in the chimera. So
can I ask you a question?
Absolutely.
Thanks. Does that depend on how many oscillators you have in the ring? So if you have a really, really big ring, you would actually see exponential rates?
That's right. I'll show you later on. We have some studies of bigger rings, but the switching rates get longer for bigger rings, so.
No, I mean, do you get actually exponent because you got all-to-all coupling? Hold on, maybe I can. It's easier if you see my finger. You got all-to-all coupling between those rings. So each node feels now the kind of noise coming from this, like through central limit theorem, coming from all those other rings. So you would actually have proper noise. Whereas if you only have like 6 oscillators, then you have got your psi noise, but you have this sort of bad noise approximation coming. So my question is, if you have really big rings, do you then go back to exponential?
The dynamics get a little bit more complicated in the case of very large rings because you end up forming local areas in the ring. So the chimeras, there's more patterns of local coherence for very large rings, and it's no longer the case that the one ring is ever fully synchronized, though that's an extremely that point is extremely sensitive to the size of the network and also the size of the noise intensity. In particular, because there's the only stable states, the only attractors in the system are the states in which one ring is totally synchronized and the other ring is asynchronous. So this is also related to my last point here, which is that we can't simulate the true dynamics in the system ever because of numerical errors. So in my previous plots here, the synchronization error always hovered around 10 to the negative 9 because that was the noise intensity that we were applying. But if we apply no noise intensity, the error will still hover around 10 to the negative 16, and that's enough to induce frequent switching in the chimera. So the question about how it actually behaved for large system size in the absence of noise is a subtle question that I don't think I can fully answer.
Thanks a lot. Thanks.
Sure. So yes, I got into this point. The reason we added noise in the first place is because the system was switching between the chimeras when we didn't add the noise because of this power law switching behavior. And we discovered that this power law switching is something interesting that we need to characterize because of that observation. So our first attempt to characterize it had to do with a random Walker model. This is just a Brownian motion sort of model. So this works only when we take a log scale. So instead of considering the synchronization errors E1 and E2, we consider epsilon, which is the log of those synchronization errors. And we assume that epsilon is undergoing some Brownian motion. And at the point at which epsilon reaches a ceiling, an error ceiling, a switch occurs and the walker starts over again. So this is the first simplest model for explaining why a switching rate might be a power law instead of an exponential. So you can see that if this was the case, then through some scaling arguments, indeed the switching rate does depend as a power law on the noise intensity. That's only a qualitative feature though. In quantitative terms, the exponent of this Walker model doesn't coincide with the exponent that we observe in the switching unless we make a more intricate Walker. So we can do things like note that it's not white noise that's acting on this. Instead, there's some correlations because there's a local Lyapunov exponent that's associated with the attractor. And you can read the paper for the details about this. But the only takeaway I want to give is that we can get Brownian sort of motion to reproduce power law scaling. But this is not the complete picture. So let me get on now to a more complete picture of the switching dynamics. So we realized that we're dealing with very symmetric networks here. They have a lot of symmetries. So in particular, each ring can be rotated by some number, and that leaves the equations invariant. So we can seek solutions which are invariant under these symmetries. So for example, here I colored all of the nodes on the left purple, and these three nodes blue, and these three nodes brown. So we can assume that the xi's for all of the same colored nodes are identical to each other. And if we plug in that ansatz into the equations, we will produce a reduced equation, which we can solve. In fact, there's dihedral symmetry in each ring, so there's a lot of symmetries. So what I plot on the left here, there's a blue attractor and an orange attractor. Those are the two subchimeras that the system switches between. So that corresponds to all of the xi's being identical in one ring and all of them being different from each other in another ring. That's one of the symmetry reductions. But this other symmetry reduction, in particular, where the oscillators form alternating groups, the attractors for that system are shown on the right plot here. There's a green one and a red one. We came to understand that the attractors for these other symmetry reductions are not attractors for the full system, so that makes them chaotic saddles. These chaotic saddles, however, interact quite intimately with the actual attractors, and the relationship between them is what gives rise to the critical switching. So let me explain that in a little bit more detail. So the way that a switch occurs can be mapped out in a route, which is typical. What we see is that the chaotic saddles lie very close to the actual attractors. So occasionally a state in the attractor will get very close to one of those saddles. And in particular, the asynchronous ring can get really close to being synchronized, and it will do so with some frequency. So whenever that happens, if a small amount of noise happened to act on the synchronous ring, then that can induce the system to move away from the synchronous state along this other invariant set. So we call this the activated state, where the noise has just pushed it slightly away from the original attractor and caused it to move closer to the invariant saddles. So this process continues, and the asynchronous ring contracts and becomes synchronized, and then finally a full switch occurs. So this can be understood in a lot of ways, which I'll go into more details next. But the important thing here is that the noise only had to act at this instance in a very small, if this ring was very close to synchrony, a very, very small amount of noise could be added here, and this could still occur. So here's an animation that I showed you before, and we can watch it just to see how this happens. You can see, especially out of this switch, those three become synchronized, and then the rings switch roles. So of course, this particular switch did that, but we did studies to show that all switches occur along this dominant pathway in our system. So here's another projection of that switching route. Here we use E1 prime and E2 prime. These are synchronization errors among the odd and odd oscillators, whereas E1 and E2 are among all oscillators. So in this case, this invariant saddle that I've been talking about, where the top ring is synchronized and the bottom ring has this alternating structure to it, this state would live in the bottom left of this plot, whereas the first subchimera lives in the top left and the second subchimera lives in the bottom right. So we did a bunch of statistics studying the trajectories that this takes in both of these projections, and to conclude that this dominant path is always the one that's activated first. So, and the other detail that can be noted from this perspective of the invariant saddles being the activated states between the switchings. The invariant saddles themselves have stable and an unstable manifold which emanates from them. So as you add a bit of noise to the original subchimera, you move towards the invariant saddle along its stable manifold, but it's an unstable state, of course. So eventually you get close to it and then you fly away from it along its unstable manifold. That was the understanding that we came to for why they switch so frequently. It's because the subchimeras, being fractal, are very, very close to the invariant sets, which are also fractals. And as such, a small amount of noise can push you off the subchimera close to the invariant saddle, and then which will then take you to another subchimera. It's interesting that the subchimera 1 and subchimera 2 in the system are the only attractors. So even though the system has nowhere else to go but these two subchimeras, but they're still extremely fragile because they're very close to these unstable states. This is quite an intricate consequence of chaos and symmetry in the system. So let me move on. If we want to make a connection with the Friedland-Winsel theory that I talked about before, we would want to try to find the path of minimum action between those two subchimeras. But as I described before, we can simply wait for the incoherent ring to cluster and become nearly synchronous, and then apply a very small perturbation to that and induce a switch. And in particular, this lambda short wavelength is the alternating perturbation that induces the switches. So when we do that for varying size of perturbation delta, there's some probability which we will induce a switch. And that probability, in fact, exhibits a power law scaling, which is identical to the power law scaling. These exponents are the same scaling exponents that the switching rate exhibits. So this is very strong evidence that this power law in the switching rate derives from this power law that's related to the closeness of this invariant saddle to the subchimeras. So in addition, if we apply this lambda as a function of delta, if we apply, the second plot here shows as a function of time, how big of a delta we have to apply in order to induce a switch between the chimeras. So you can see that depending on the time, sometimes we can apply a very small delta, and sometimes we have to apply a very large delta. This has to do with the chaotic nature of the attractor. The attractor will visit states which are clustered at different periods, and we have to wait a very long time before it will visit a state which is very closely clustered. When it visits that state, we can apply an extremely small amount of noise or extremely small perturbation in order to induce a switch. So we come to understand that there is no minimum action path connecting the two subchimeras. Instead, there's always a path of smaller action that can be found if one waits a longer amount of time before applying your perturbation to it. So this is an interesting property of stability in these attractors. Yeah. So let me pause in our discussion to make some relation to critical phenomenon, because this is, of course, most people know power law from statistical mechanical systems which exhibit second order phase transitions. So in particular, there's some analogies that we can make. In percolation models, for example, the correlations decay exponentially for the subcritical occupation probabilities. But when you hit the critical occupation probability, those correlations start to exhibit a power law instead. And that happens exactly when the correlation length in the system diverges. So at that point, there are finite clusters of all sizes in the system. So there's a strong analogy in our system. There are finite barriers in the actions that's required to induce a switch between the two subchimeras, exactly when the inverse of the quasi-potential diverges. The inverse of the quasi-potential is going to play the same role as the correlation length. So it's intriguing that for our system, there's no tuning that's required to reach this critical behavior. And instead, the system is criticality is self-organized. It emerges without tuning any parameters. So anyways, people have interest in self-criticality, but this is a new version of it in this coupled oscillator context. Okay, so last point about the chaos in the system here. This behavior is related to what are called riddled basins of attraction. So what's plotted here is the phase space. This is a slice in the phase space, ring 1, oscillator 6 versus ring 2, oscillator 6. And these are points which are attracted to subchimera A in blue and subchimera B in orange. So you can see that the basins of attraction for these subchimeras are actually the entire fractal phase space. The basin of attraction for the orange chimera gets arbitrarily close to that of the blue chimera, and no matter how much we zoom in, there's always points which will be attracted to the blue chimera versus the orange chimera. So Ott and others characterized when riddled basins of attraction occur quite clearly. It has to do with dynamical systems that have symmetry like our system has. So here's another depiction of those riddled basins in a particular coordinate slice. In this depiction, we take the vector of x's to be connected by the short wavelength perturbation that I was talking about before. So delta equals 0 corresponds to the orange subchimera. Delta equals 0.2 corresponds to the blue subchimera. So you can see that as you get closer to the top or closer to the bottom, the system gets more and more orange or blue because you're getting closer to the chimera. But there are these protrusions that get arbitrarily close to delta equals 0. And the intermingling of those basins with the attractors themselves is what's giving rise to the power law switchings that we observed. Okay, so finally, we feel that we had a pretty good theoretical understanding, but we wanted to verify that these things actually exist. So we asked our experimental friends at Maryland, and they conducted experiments on optoelectrical oscillators. These are not logistic maps, but this function I is a particular function that describes the physics of these optical oscillators. But nevertheless, we can model these systems. We can predict that the same switching chimera sort of behavior occurs, and the experiments confirmed it. So I'll play the video here of, this is the experimental data showing oscillators in one ring switch. And not only do they switch, but they have the same power law scaling that we were so interested in the logistic map. So we are confident that this is a phenomenon which is universal in the sense that it can be realized in different systems, and it's characterized by the symmetry in the system. A few more details about that. As George asked in the beginning, there's the obvious question of how the system depends on the ring size. So we did some studies with increasing ring size n. Let me describe all the things that are shown here. This random initial conditions will give rise, or random parameters, I'm sorry, will give rise to either one of these states: incoherence, switching chimeras, non-switching chimeras, chimeras death, or synchronization. The bottom plot here shows in the parameter space where each of these behaviors occur for rings with, this is 21, 24, and 27 oscillators, I believe. So as we increase the size of the rings, what we're noting is that there are more non-switching chimeras. They start to take over a greater portion of the parameter space, but the switching chimeras still exhibit a sizable portion. Though as you take the ring size to infinity, most likely the non-switching chimeras will overtake the system. Yes, another thing to note is that the switching time for the the scaling exponents tend to, let me interpret this after looking at it. So the switching is always power law, but the switching rate is itself growing as a power law with the ring size. Okay, so that's interesting too. Okay, anyways, last point about universality. We wanted to know whether this was strictly occurring because the dynamics were discrete in time, but it turns out that that's not the case. We were able to find Rossler oscillators, which have continuous time dynamics, which exhibit the same sort of switching behavior. So you can see here, the top ring is synchronized, Rossler oscillators, the bottom ring is asynchronous. And after very long periods, the rings will switch. So you have an alarm here. So I guess that means I'm getting close to my time limit, which is good because I'm at my conclusions. Our results highlight that chaos in the system, along with the symmetry in the system, can qualitatively alter stochastic switching that had been previously thought to be exponential, and make it a power law instead. And we have some speculations about which sort of natural systems it can occur in, including some of these interhemispheric switching scenarios that people like to talk about. And we also make a note that this chimera might even be exploited as a detector for very small noise. So since the very small noise will cause the switching rate to sensitively vary, if we created this in reality and we're able to couple this system to some physical system, we can infer the amount of noise in that physical system by looking at the switching rate in the rings. So those were our conclusions. I want to thank our funding agencies. This is Army Research Office and Office of Naval Research. And also thanks to all our my co-authors again, Yan Zhao especially, first author on this paper, put a lot of work into it.